Okay, so I went on the good old internet and I found a picture of three space lines and how they can intersect. So this is parallel lines that stay the same distance apart and never cross. This is the intersecting lines that cross at one point. This is actually the same. It's perpendicular lines. It is a special example of intersecting lines, only they intersect at 90 degrees. And here are your skew lines. So in order to understand what skew lines are, you should kind of understand what planes are. And I don't mean airplanes, I mean planes. Planes go on forever in 2 dimensions. So imagine a piece of paper. So here's a piece of paper. And it just goes on infinitely left, right, up, down. And because you can hold the piece of paper at any angle whatsoever, that makes multiple different planes. So right now I'm wandering my cursor around a tablet and I'm sitting upright on my couch. I am now, don't know if you can tell from my voice, I'm now leaning back. So my laptop or my tablet is at about a 45-degree angle. Not that you can tell, except maybe my voice changed in distance from the speaker. But now my plane is sitting at a different angle. So that's what a plane is. So if you've got your airplanes at different heights, that means you've got parallel planes, but you don't have matching lines. So let's go on. I do not have a picture of this. I don't have a picture of this in any of the notes, but you're welcome to Google just like I did, or steal it. There, I'll move my mouse out of the way by taking a picture of whatever when you've paused this. So the next thing we look at in this course is equations of planes in R3. So we've done equations of lines in R2. Then we've extended upon that by doing equations of lines in R3. Now we're going to do equations of planes in R3. And you can't do planes in R2. So a specific plane in R3, so in 3 space, can be described by 3 non-collinear points that lie on a plane. So you've got 3 points, so 3 dots on a piece of paper, which is different than if you had a dot on a piece of paper, a dot on a piece of paper, and then you had a dot like hanging above the piece of paper somehow. So this is 3 dots on a piece of paper. They're non-collinear, meaning they all don't lie in a straight line. So they kind of make a triangle. And what you need to know is what I said before, and that is a plane is infinitely long and infinitely wide. But in order to describe this plane with an equation, you need at least 3 non-collinear points. Now we have to do stuff with these points. So from the information given from those 3 points, we can describe the slant of a plane. So we can describe the slant using 2 direction vectors. So for instance, I usually pick a point. So in this case, I'll pick point A, and I'll do a direction vector AB, and I'll do a direction vector AC. I try not to make things complicated. Then we can specify a point. And of course, we can use point A, or we can use point B, or we can use point C, or if there's a point D, you can use a point D. So that makes this non-unique as well. So you need a point, and I've probably got this written somewhere. You need a point, and you need 2 direction vectors. They both can't be called M, just so you know. So I'm going to erase this and keep reading. So the plane passing, oh, there's my perfect example. The plane passing through the point P, x1, y1, z1, so a point, and then associated back to the origin in 3 space, which is 0, 0, 0, turns that into what's called a position vector. So the same information in the x, y, and z spots, but these are coordinates, these are components, and having non-collinear direction vectors. So not, I don't know if I've locked this in, you can't have, I have locked it in, you can't have a direction vector going here and then another one going there. You can't have them parallel. And you can't have them collinear, meaning you can't have A, B, C lying in a straight line. So you'll have two direction vectors. We call them M1 and M2 with their vector hats. And you make a vector equation. Again, it's an expansion of the equation of a line. So an equation of a line in 3 space would have stopped here. You would have had a point written as a vector because it's a position vector now. You would have had a parameter, and you would have had a direction vector. When you're talking about a plane, you have the same setup plus some. A point, position vector, a direction vector, a second direction vector. So you need 2 parameters, in which case I can't say t is an element of the real number. I say t and k, in this case, are elements of a real number. Then you can make some parametric equations. So you can say, okay, x is equal to x1 plus t times the a1 in your direction vector plus k times the a2 in your direction of the second direction vector. And then you do the same thing for the y's, and you do the same thing for the z's. So try not to get confused with lines and planes, because planes need more information because they are more complicated looking. This blue thing is a line, this purple thing is a plane. Way more complicated. All right, so let's look at a question. Of course, there's information on the next slide. So I'm going to move this out of the way. See how much space I need. So it says determine vector and parametric equations for the plane passing through the points. A, 1, 7, 2, B, 4, -5, -1, and C, 3, 8, -6. So I am going to choose to make direction vector 1, AB, and I'm going to choose to make direction vector 2, AC. It really doesn't matter what you do as long as you have 2 of them, 2 different. So I can't do AB and BA. That's not different. So AB means I list B first and A second, and then I subtract. So 4 minus 1, -5 minus 7, -1 minus 2. And because this is a vector, I can choose to reduce it, just making it a shorter vector, but in the exact same direction. Now I'm going to do the same thing here, and yes, I see that I've got information on the next slide. So this one means I need to write down C, and then A, and then subtract. So 2, 1, -8. No reducing here. So because you can pick 2 different direction vectors than I can, and you can pick a totally different point from me, our vector and parametric equations for planes are not unique. So I'm about to do my answer for vector. I'm going to use R because this is long. So I'm going to choose the point to work with is 1, 7, 2. Make myself laugh. Plus t, and then I get to pick one of the 2 direction vectors. The order doesn't matter, so I'm going to pick the first one first. And then another parameter, and the second direction vector, or the other direction vector. And technically, those aren't pulled out of anywhere, they're part of an R. And then, obviously not enough room, I can take those vector equations and I can turn them into that vector equation singular, and I can turn them into parametric equations, plural. So x is equal to 1 plus 1t plus 2 times k. Y is equal to 7 minus 4t plus 1k. Z is equal to 2 minus t minus 8k. And those are your parametric equations. I'm not going to write this down again. So now let's see what we have to do with these parametric or vector equations. First thing says determine the coordinates of a fourth point on the line. So what you cannot do is you cannot create a fourth point that is the same as one of the other 3 points. So we have to be very careful in our t and k selection. So something you're not allowed to do is you're not allowed to use t is 0 and k is 0 at the same time, because then you're just going to make 172, and 172 is point A. So what you might want to do, and you have to kind of play around with it a little bit, you're totally allowed to say, okay, t is equal to 0 and k is equal to 1. Before I solidify that choice, I'm going to see what that does. So what that does is it makes this be 0, and I end up with 1 plus 2, which is 3, for the x. That means I'm making that point. Bad pick. How about if I reverse it? It'll be 1 plus 1, which is 2 for the x. Hey, that works. I thought I was going to get b, but I don't. So that's what I'm going with. So you do have to do a little bit of figuring before you start to make sure that you aren't doing too much work for no reason at all. So now I'm going to do it formally. And of course you can use the vector equation to do it, but I'm not going to. So it's 1 plus 1 plus 2 times 0. 7 minus 4 times 1 plus 0. 2 minus 1 minus 8 times 0. 1 plus 1 plus 0 is equal to 2. 7 minus 4 plus 0 is equal to 3. 2 minus 1 minus 0 is equal to 1. Therefore, D is 2, 3, 1 coordinates with round brackets. All right, next question. Determine whether R, which is 3, 7, negative 2, lies on the plane. So it's not one of these, and it's not the point that I just made. So I'm going to take these things individually, and I'm going to see if I can figure out whether R is on the plane or not. So I should put 3 in for the x. And I should clean this up. So 1 on the other side is subtract. So I end up with this. Then I'm going to steal this one. I'm going to put 7 in for the y. And I'm going to clean it up. So 7 on the other side will be subtract, so that's 0 equals, I'm going to say k minus 4t because I like my positives first. And then last of all, my z. Clone. My z will be substituted with the negative 2, and then I'll clean it up. And there's no avoiding negatives in this one. Oh, there is. It's all negative, and all negative is the same thing as all positive because we can multiply everything by -1. That works well. So the problem with this is that we've got 3 equations and 2 unknowns. So what we need to do is we need to solve for t, excuse me, couldn't catch that, t and k. So you can pick any 2. I'm going to pick these 2. And you get to do grade 10 elimination and substitution. Have I ever told you before that the problem with grade 12 math is that you need to know all the math that came before today? I'm going to cough again. I'll be back. Too much talking. All right. So t plus 2k is equal to 2. And k minus 4t is equal to 0. I'm going to do substitution. I'm going to take this 4t across the equal sign and make it positive, adding on to a 0. Then I'm going to replace this k with 4t, but everything else is going to stay the same. And I end up with 9t equals 2, which means t is equal to 2 over 9. Oh! Which I get to substitute back in here. And get that k is equal to 8 over 9. So what I've done is I've made sure that my x and my y work. Well, this isn't for sure until you make sure that your z works. So what we need to do now is we need to take the third one, the one that we overlooked, the third part, which in my case is z, and we need to put in t is equal to 2 over 9, and k is equal to 8 over 9, and we need to see if this equals the 4 that's on the other side. So we need to do a left side, right side check. So left side is equal to 4, right side is equal to 2 over 9, plus 8 times 8 over 9. So that's 2 over 9 plus 64 over 9, which is 68 over 9. No, it's not. It's 66 over 9, and 66 over 9 is not equal to 4. So we made 2 of the 3 parts work, but then the third part doesn't work. So therefore, R is, I'm going to say R is not on the plane. R does not lie in the plane, meaning that point R is not sitting on our piece of paper defined by this or this. So let's see what the important information on the next page is. Vector equations and parametric equations are not unique for planes. We could have used a different point, so I used point A. If you had used point B, you have a totally different solution. We could have used a different point, and I decided to make AB and AC. If somebody else made CA and CB, that is completely different, so your answers are not unique. You choose any values for T and K to find your fourth point. And for the last part, use 2 of the 3 equations to solve for T and K, and then you check in the unused equation. So for part A, it's that. For part B, those are the notes. For part C, those are the notes. And if I refer back, part C There's us solving for t and k in two of the equations and checking it in the third. So those are your important notes on the following page. Let's see what comes after this. An alternate solution is doing this. We will get to stuff that looks like this. Let's do it now just to remind you about this stuff. So if point R lies on the plane, vector AR will lie on the plane. So when translated tail to tail, vector AR and M1 and M2 are coplanar, meaning that they are in the same plane. So this is a check. This is a check to see if a point is in a plane. I'm going to show you how to do it, only so I go over the different pieces of information necessary for cross product and dot product. And spelling. I probably would not go through this procedure because I would never remember that I could do that. Whereas what I did in part C here was, I'm going to call it basic math because it was grade 10 math. And grade 10 is basic compared to grade 12. So what I need to steal is this, my direction vector 1. It's this, my direction vector 2. I need point A, 172. And the test point, which is point R, and point R is 3, 7, negative 2. So, first thing I have to do, apparently, is take my M1 and M2 and do the cross product. And it doesn't matter what order I do it in, so I don't know which one of these is M1 and which one is M2 right now, and I don't care. What matters is that I do the cross product with them, so I'm pulling this off right now. So to do cross product again, 2, 1, negative 8, 2, 1, negative 8, 1, negative 4, negative 1, 1, negative 4, negative 1, scribble, 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 and then truly scribble. So down to the right, minus down to the left. Down to the right, minus down to the left. Down to the right, minus down to the left. So the result of that bracket is vector negative 33, negative 6, negative 9. And of course, if I felt like it, I could reduce that because that is a vector perpendicular to the two vectors I had. So I'm going to choose to do that because I have more math. So I can divide them all by 3, and even better, I can divide them all by negative 3. There. Whew, I like that so much better. All right, the next thing I have to do is I have to find AR. So that means I'm going to take this stuff down into a working space. So A and R. Of course, that doesn't work out well. Here we go. And then the last thing I have to do is I have to do the dot product to see if it's 0. And I should end up, because R was not on the plane, I should end up with a non-zero, meaning something other than 0. So M1 crossed with M2 dotted with AR equals 11, 2, 3 dotted with 2, 0, negative 4, which is equal to 22 plus 0 plus negative 12, which is equal to 10, and 10 is not equal to 0, therefore R is not on the plane. So I would not recommend this method, and the reason I wouldn't recommend this method is because there is an element of memorization to it, and an element of trying to picture things in 3 space, which I can't exactly diagram on a 2-space smartboard document. What I can do is remind you of all the skills and vectors that came before this that you may have to use in certain places, or could use, I guess, is a better example of a word for this. So there's the stuff. This is not a case of being R2 and R3, and the reason I say that is because you can't have planes in R2, you can only have planes in R3. So, but this is the work associated with equations of planes in R3. Best of luck. Ask me questions.